So any questions on the homework? Moving to chapter 5, diagonalization.
Will the solutions be posted?
Do you want the solutions to be posted?
Yes, please.
Sure. I mean, nobody asked for that before. I can always
yeah,
post the
we can watch
solution.
that.
No, I can always post the solutions. That's not a problem. So this homework in particular was it?
Yeah.
Okay, I'll post the solutions then. You take a look and let me know what you think. Okay. Yeah.
It was, I think, 19 part B.
On which
It
page?
said it wanted to verify LA phi sub beta M equals phi sub beta T. Yeah, sure. That's page 108. Phi greater than phi per page 105.
Who's gamma? Page 105 or 108?
I was trying to do a callback to verify.
LA phi beta is phi gamma T. And you checked with beta and it's not working, or what?
It doesn't work per se, but
Because I see that they only want you to check it for that certain matrix M. So when you send me back to page 105,
it was just
it holds in general, I see, the one with phi gamma. So the one they want you to check is for a certain matrix, so that would make me think that. But again, I didn't go into the details and computational part, so I would assume it's pretty computational, this one, I would say.
yeah.
Mhm. But yeah, I'll look into it, I'll post the solutions, and we'll see what happens. Okay, so we're starting chapter 5. So by definition, an operator is called diagonalizable if its matrix T beta in some ordered basis beta is a diagonal matrix. So as long as there exists such an ordered basis beta, such that the matrix of T is diagonal, then the operator is called diagonalizable. And something similar happens for matrices, in the sense that a matrix is called diagonalizable provided that the left multiplication by A operator is diagonalizable. Okay, so what does this exactly mean? So let's say that T from V is diagonalizable. So according to the definition, the matrix of T in some basis beta is diagonal. So beta, let's say, is V1, V2 up to Vn, if the dimension of V would be n. So there exists such a basis such that the matrix of T in that basis is a diagonal matrix. So now a diagonal matrix, it would have to be n by n, right, if V has dimension n. So it would have some entries on the diagonal, right? Everywhere else it would be 0. So let me call those entries lambda 1, lambda 2, lambda n. And then everything else would be 0. Right, so it would have to look like this. Then if we think about the way in which the matrix of a linear operator is computed, if I refer to this matrix as A, let's say, then T of Vj was the sum I equals 1 to n Aij Vi, right? The matrix. Aij would be the entries of the matrix A. But that matrix A is very special, so only the diagonal entries are maybe non-zero. Everything else is 0. So a diagonal entry is exactly where I and j are equal, right? So among all those i's from 1 to n, I only need a, j, j. So when I equals j, because everything else would be 0. And a, j, j is something that in the picture above here we called lambda j. Okay. And that should hold for every vector in the basis beta. Okay, so the vectors have this property which turns them into what we call eigenvectors for a linear transformation or a matrix. Note that vectors will have to be non-zero. They have to be non-zero because they are part of a basis, right? A basis cannot contain the zero vector, otherwise it would not be independent anymore, right? Okay. So when it's diagonalizable, this should happen. All the elements of the basis should have this property, which is defined here. So a non-zero vector V is called an eigenvector of an operator T if there exists a scalar lambda such that T of V equals lambda V. Above there, let me see if I can move this thing back up so we can see both. Okay, so so the lambda, the scalar lambda from the definition would now be that jth entry on the diagonal of the matrix. And the scalar lambda has the name, receives the name of an eigenvalue. Okay, so non-zero vector is eigenvector if T of V is lambda V, and lambda is called the eigenvalue corresponding to the eigenvector V. Similarly for matrices, an eigenvector of a matrix is an eigenvector of this linear transformation L sub A. What does that mean? It means that L sub A of V equals lambda times V, right, to be an eigenvector for L sub A. But L sub A of V is multiplication by the matrix A. So this is just A times V equals lambda V, and that's exactly what they have listed here. So to be an eigenvector for a matrix, you need A times V equals lambda V. And then lambda again is called the eigenvalue of the matrix corresponding to the eigenvector V. Anyways, we keep in mind that eigenvectors are not allowed to be 0. All right, so let's try to rewrite everything that we've seen so far. So we've seen that in case that an operator is diagonalizable or a matrix, that thing up there should happen, right? So every element of that basis should be an eigenvector. So we can kind of translate that definition into this theorem here, which says that operator is diagonalizable if and only if there exists an ordered basis beta for V consisting of eigenvectors for T, right? Because that's exactly what we've seen that will happen. That basis that should exist will consist of eigenvectors, right? Every element in the basis will have this property. Furthermore, if T is diagonalizable and that is beta, V1 through Vn, and D is T beta, then D is diagonal, right? Because that's what started everything. And Djj, what we called lambda j up there, is the eigenvalue corresponding to Vj. So this Djj, we denoted by lambda j up there. Okay, so if we want to diagonalize a matrix or a linear transformation, all we have to do is to find this base in which the matrix corresponding to T is diagonal. And then find the corresponding eigenvalue. So here's an example of a diagonalizable matrix. So this matrix will turn out to be diagonalizable with that equal to the vectors and 1, -1. That would be a basis of eigenvectors of A. A basis of R2, right? Because you're going to look at A or L sub A as a linear transformation from R2 into R2, right? So being A being diagonalizable or L sub A being diagonalizable is the same thing. So let's see what happens. What would be L sub A in the basis beta? Right, so the claim is that this basis will make L sub A in basis beta a diagonal matrix. Okay, so how do I find this matrix? Well, I'm going to apply L sub A to the first vector, 2, 3. L sub A is left multiplication by A, so this is 1, 2, 3, 2, 2, 3. That's 2 plus 6, so 8. 6 plus 6, 12. All right, but that's exactly 4 times the vector 2, 3. So the first vector, this one, V1, turns out into 4 times V1, turns into 4 times V1. So 4 is that value of lambda 1 that we talked about before, the scalar. And L sub, and that makes the first column of the matrix 4, 0, right? 4 times the first vector in the basis plus 0 times the second vector. So the first column is 4, 0. And then L sub A of 1, -1. Is what? -1, 1. So -1 times the original vector. So L sub A of V2 is -1 times V2, which makes this column here. So pretty much we got a diagonal matrix with lambda 1 equal to 4 and lambda 2 equal to -1, right? Those would be the eigenvalues of the matrix A or of the transformation L sub A. It is the same thing. So this is a diagonal matrix. So hence the original matrix is diagonalizable. So pretty nice and easy.
Where did you get the beta?
That's exactly what I was going to say. Pretty nice and easy if beta is given, right? That's just straightforward. But this will be our main first to actually get the vectors in beta. And well, once we have the vectors, you see that it's pretty easy to get the eigenvalues 4 and -1 there, right? So we'll take a look now into how to actually get them. Okay, so I'll look at matrices now. So let's say that V is an eigenvector of a matrix A. What that means, according to the definition, is that it is in fact an eigenvector for L sub A. That's how it was defined. So L sub A of V equals lambda V. Well, V has to be non-zero, first of all. So equals lambda B for some scalar lambda. All right, but L sub A of V, L sub A is just a tool in the end, because it's just multiplication by A, so we can turn this into a main kind of identity. So basically we have that A times V equals lambda V. Now if we move everything to the left, AV minus lambda V equals the 0 vector, right? Okay, I can factor out the vector V on the right. A minus lambda identity matrix n by n, all times V equals 0. I cannot say A minus lambda, right? Because A is a matrix and lambda is a number. That's why I put the identity matrix there. Okay. So now we're going to appeal to your undergrad linear algebra knowledge. So what we have here is in fact a homogeneous system of linear equations, right? It's a system where you have zeros on the right. Every equation has a 0 on the right. Now such a system has always at least one solution, the 0 solution, correct? So it's always a consistent system. The question is, does it have only the 0? Does it have infinitely many solutions, right? So now, we want this system to have infinitely many solutions. Why is that? Because we want this vector V to exist and to be non-zero at the same time, right? We don't want the only solution of this to be V equals 0, because then we have no eigenvectors, right? We need to have non-zero eigenvectors, non-zero vectors with that property. So this is a system that is consistent with infinitely many solutions. Okay. Again, back in undergrad linear algebra, we've seen that this is equivalent to this matrix here being not invertible. Why is that? Well, if this matrix A minus lambda identity would be invertible, then in this equation here, I can just go ahead and multiply by its inverse to the left, both sides. What would happen? Okay, so you're going to just get V equals 0, right? If you multiply by the inverse of A minus lambda identity to the left. And that's right. We know that V has to be non-zero. So that will be equivalent to A minus lambda identity not invertible. And in terms of the determinant, there is an equivalent way to read being not invertible is equivalent to what? Being 0. Okay, so here's the plan. It's all if and only if, right? So the lambdas are completely described by this identity here. Determinant of A minus lambda identity has to be 0. That will be an equation, right? Determinant is a number after all, right? We know theoretically how to compute any determinant. If we have the lambdas, then the next step will be how to find the eigenvectors, right? If we know lambdas. Because in the example above here, it was kind of backwards. You were given the eigenvectors, and that was the simplest way to look at it, because once you have the eigenvector, you multiply by A and get the eigenvalue immediately, right? Now the question is that kind of backwards already, right? If I give you the eigenvalue, how do you find the eigenvector? But still, we don't have the eigenvalues yet, so let's continue from here. All right, so so we need to solve this kind of equation to find the eigenvalues, right? This is what defines the characteristic equation or the characteristic polynomial, right, in general. So definition. Let's see if so definition, let A be a matrix then f of t defined by the determinant of A minus t identity is called the characteristic polynomial of A. This up there, lambda is going to be an eigenvalue of A. If and only if we said determinant of A minus lambda identity is 0, so f of lambda is 0, right? Where f of t is the thing defined above. So lambda is a 0 of the characteristic polynomial. So the plan is simple then, right? Given the matrix, we can find its characteristic polynomial and then find all the zeros, right? Easy to say, but if the polynomial has degree more than 2, it's not that easy, right, to do that, but still. So, for example, let's find the eigenvalues of this matrix here, 1, 2, 3, 2, the one that was given before. Okay, so we need the characteristic polynomial of A, f of t. Determinant of A minus t identity, we're in 2 by 2 right now. So it's basically the determinant of the matrix 1, 2, 3, 2 minus t identity is t0, 0, t. So we end up with a determinant of 1 minus t, 2, 3, 2 minus t. It's a 2 by 2 matrix, very easy. The determinant will be t times 2 minus t minus 3 times 2, which is 6. And it's a second degree polynomial. I need to find its zeros, so let me multiply it through there. So t squared minus 2t minus t minus 3t plus 2 minus 6 minus 4. And this factors, right? T minus 4, t plus 1. So lambda 1, let's say, is 4. Lambda 2 is negative 1. Usually the order is not important. However, in matrix theory, it's customary to list them in decreasing order. So lambda 1 would be the highest that you see, but it's not important at this stage. And if you think back, I mean, if you look back at this example here, that's exactly what we got. I mean, we knew the eigenvectors back then, but 4 and negative 1 were there. Okay, so what can we see based on this example? We had a 2 by 2 matrix, and we got a characteristic polynomial of degree 2, right? Which has how many zeros? Well, this one had 2 of them, but in general, you have at most 2 zeros. You just have one that is repeated, or it can happen that you have none, right? If it's a polynomial with complex roots and you don't want to deal with complex eigenvalues, which again, it's possible, right? If you're allowing things to be complex, if the field is the field of complex numbers, then any polynomial will have n roots. Okay, so in general, if you have a matrix that is n by n, right? The characteristic polynomial will have degree n. And you can look a little bit into the matrix that gives you the determinant, because that will tell you a little bit about what you actually get. So matrix A, let's say, has entries Aij. So when I subtract t times identity, I'm actually subtracting t from the diagonal entries only, right? So I get minus t, and then the other entries of this row would be the original entries of A. And then A 2, 1, A 2, 2 minus t, A 2n, A n1, A n2, A nn minus t. Okay, so this is what we call f of t. So f of t is a polynomial of degree n. What is the leading coefficient of that polynomial? So the coefficient of t to the power n. Well, imagine how that determinant is computed. You don't have to actually compute it, but imagine expanding along the first row and getting n minus 1 by n minus 1 determinants, and then expanding along the second and so on. To track t to the n, how can we get t to the n out of those products? Well, if I'm using this entry, right, expansion, so then that would be multiplied by the determinant of this one. And then I'm doing the row 1 expansion again, and I'm going to use that specific entry, and so on. So to get t to the n, I can only get it in one way, from the multiplication of, somewhere in that sum of products of whatever it is inside that determinant, which is not very nice what will happen in there. But somewhere you will have the product of all those diagonal entries in that sum. And that's the only term that will give you t to the power n. And t to the power n will have the coefficient negative 1 times negative 1 times negative 1 n times. So the coefficient is just negative 1 to the n. Okay. And then it would be something times t to the n minus 1 plus a1 t plus a0. Now a0 is something else that I can tell something special about. A sub 0 is. How can you get rid of all the other terms? You can set t equal to 0, right? So a sub 0 is the same as f of 0. Who is f of 0? Well, if you that's the determinant of the original matrix A. The free coefficient here is the determinant of A. And there are more things that could be said, like for instance, and I'll look into the book, maybe there are some homework questions that you can get here. There is a connection between this and the trace of the original matrix, the sum of the diagonal entries there. So, okay, one more example that we're going to need a bit later. Example 2. So let's say that two matrices, two n by n matrices are similar. Remind you, that means that one of them can be written as M, B, M inverse for some invertible matrix B. Matrix M, sorry. And we looked into this last time, and we've seen that if we take two similar matrices, then they will have the same determinant, right? That's the thing we looked into. It's been a while, a week ago, but that's what we talked about then. So now it turns out that there is more than this to similar matrices. Not only that they have the same determinant, but they have exactly the same eigenvalues and exactly the same exactly the same characteristic polynomial. Okay, why is that? Let f sub a, let's say, of t be the characteristic polynomial of A. Okay. But A, we said, is the same as M, B, M inverse. They are similar. Okay. So here's what I'm going to do. Identity matrix, I'm going to replace it by M times M inverse, right? It's the same thing. And I'm going to factor out M on the left, M inverse on the right, right? With factors, multiplication is not commutative, so I'll keep things where they are, left and right. And then in the middle, I will get B minus P, the identity. Okay. If you multiply this one through, you get exactly the thing above. All right, but now the determinant distributes over matrix product. So this is determinant of M times the determinant of B minus T identity times the determinant of M inverse. Okay, but we've seen that the determinant of the inverse of a matrix is 1 over the original determinant. So those two expressions here will cancel out. So we're left with determinant of B minus T identity, and what's, well, that's exactly what we would call the characteristic of the matrix B. So A and B have the same size, n by n, have the same characteristic polynomial, right? The polynomial, therefore, will have the same zeros. So A and B have the same eigenvalues. Okay. Keep this in mind. So we know how to find the eigenvalues of a matrix, right? How do we find the eigenvalues of a linear transformation? Because you see how we define, the eigenvalues came from the zero of a polynomial, right? And what was the polynomial? Determinant of A minus the identity is the determinant of a matrix, right? And if you start with a linear transformation, what would you use there, right? That's the main question. Here's the idea. That's the definition here. So if you start with a linear operator, by the way, a linear operator is, by definition, a transformation of space into itself. So from V to V, then it's called a linear operator instead of a transformation. Write this down. Domain and the codomain are the same. Right, so T is a linear operator. Then we define the characteristic polynomial of T. Characteristic polynomial of T. So pretty much f of T is the determinant of A minus T identity. Now, what matrix is that? It is the matrix of T in some basis beta. Which basis? I don't know, any basis, they say, right? But if the definition is calling for any kind of basis and any kind of matrix in there, then it makes sense to ask the question, doesn't it matter which matrix and which basis we choose, right? Because if you choose another basis, you end up with a different matrix, and maybe the determinant of that matrix minus T identity is different from the determinant of this matrix minus T identity, and maybe the definition doesn't make any sense then, right? Now, of course, it makes sense, and the idea is that it doesn't matter which matrix you choose, and it doesn't matter which basis beta you choose, and that's what we're going to look into next. The definition above is independent of the choice of basis beta. And in order to justify, so we'll actually give a proof of this, but in order to justify this, I'm going to need to go back a bit. I was telling you a while ago that there is this notion of a change of coordinate matrix. I'm going to need it now, so I'll go back and take a look into that. So let's look at this idea of the change of coordinate matrix. Let's say that V is a vector space. And let's say we're looking at two possible bases on V, beta and beta prime. The change of coordinate matrix, it's usually called Q, defined to be the identity transformation on V. The identity transformation is the one that maps X to itself for any vector X, right? So identity of X is X. So the identity transformation, the matrix transformation from beta prime to beta. So for example, just to see exactly what this does. Let's say V is R2. I'm going to pick two bases in R2 for R2. Remember that R2, in order to choose a basis, I can throw in any two vectors that are non-multiples of each other, right? So as long as I have two vectors that are not multiple of each other, so I'm fine. So what I have here are those two vectors for beta, and these two vectors for beta prime, 2, 4, 3, 1. Okay, so I want to see what that matrix Q looks like and what exactly does it do. So Q is the identity from beta prime to beta. So to find this matrix from beta prime to beta, what I have to do is to apply the transformation inside, which is the identity in beta prime, because it's asking from beta prime to beta. So I'm going to apply it to 2, 4. Well, it's the identity transformation. Nothing changes. So apply to 2, 4 is 2, 4, right? But it's asking me to go from beta prime. Yes, I took 2, 4, and 4 has to be expressed in terms as a linear combination of the vectors. So what is that linear combination? I have it here. You don't have to think too hard. It's 3, 1, 1. 3 times the vector 1, 1, minus 1 times the vector 1, negative 1. Will give you 2, 4. And if I do the other one, identity applied to the second vector in beta prime gives me 3, 1 again. And 3, 1 as a combination of the vectors in beta is 2 and 1. So that matrix Q, or the matrix of the identity from beta, has its given by the coefficients, right, of the first vector expression in the basis beta, so 3, negative 1. That's the first column. And then the second column is 2, 1. Okay, so that would be the change of coordinate matrix, but what exactly does it do? Well, here's what it does. It's going to change for any vector you choose, beta into beta coordinates in the following sense. If I take a vector like 5, 5, if I express this in the basis beta, like I take the beta coordinates of this 5, 5, what do I get? What vector do I get? Well, 5, 5 can be expressed as 5 times the first vector in beta plus 0 times the second vector in beta, right? 5 times 1, 1 plus 0 times 1, negative 1. And 5 beta prime coordinates would be what? How can I get 5, 5? Well, it wasn't an arbitrary choice. It's pretty easy to get 5, 5 out of 2, 4, and 3, 1. You just add them up, right? So the coordinates in beta prime will be 1 and 1. So we said the matrix Q changes beta prime coordinates into beta coordinates. It goes from beta prime to beta, which means that exactly this should happen. This is the beta prime coordinate that I wrote here of my vector. I should get the beta coordinate of the same vector by multiplication with that matrix. It better be. It is, yeah. So it basically changes coordinate basis. That's what it does. Note that this matrix here, if you compute its determinant, is going to be non-zero, so it's invertible, right? It's 3 plus 2, so 5. This Q is invertible, but it's going to be invertible in general. And the reason it is invertible, it's because we've seen a while ago that the matrix associated to an invertible transformation has to be an invertible matrix, and the identity as a function is invertible, right? So this matrix is invertible since the identity is invertible as a linear transformation or as a function. Okay, and where I'm trying to go with this is the following. I'm not done with this matrix. So far we just define it. We know we know what it does. But here is, so the next remark is how it actually affects a linear transformation. So this is a theorem, let's say. So let T be a linear operator on V, so T from V to V be a linear transformation. V is finite dimensional. By the way, everything that I'm saying here about transformations is in a finite dimensional setting, because that's when the matrix of a transformation will be an n by n, finite matrix. Otherwise, it doesn't talk about all this. It's finite dimensional. Beta and beta prime are both ordered basis. For V. Q is the change of coordinate matrix, the one that changes beta prime coordinates into beta. So identity, the matrix of the identity transformation from beta prime to beta. Then we have the following identity. And this is actually what we need in order to check that definition for the characteristic polynomial is independent of the choice of beta. The matrix of T in the basis beta prime, so going from beta prime to beta prime, equals Q inverse times the matrix of T in the basis beta times Q. Now, before we go ahead and prove this, let's make sure that that's exactly what we need. If I go back, here, I don't know if you can read that. A was the matrix of T in the basis beta, right? And the definition called for the determinant of A, which is T beta minus T identity, right? And the question was, is this the same as the determinant of T beta prime minus